put it anywhere you want, and what translate does is translates it to a number that's going to be in the table. So you can put it anywhere you want. I agree that psychologically, yeah, you think of the dollar sign at the end. But what is the other thing you need? So you need to get this table filled in. You know, it should more or less the caret, this caret line would look a lot like, say, a plus or a minus, or you know, but you need to pay attention a little bit to precedence. So there's two things. Two plus 3 plus 4 as compared with 2 caret 3 caret 2. We want to keep the numbers relatively small. Here, when we get to this plus, when that's the incoming, the I stack is going to have on it the 2 and the 3. The I and the O stack has on it the sharp on the bottom, this first plus here, and now we're to this, and so the incoming is a plus, and we've got a plus on top, and so you can see what we do. When the incoming is a plus, and there's a plus on top of the stack, right here. Okay, so the incoming is a plus, and what's on top of the stack is a plus. You do a 2. That is, we are going to pop this guy off, so it's gone. We're going to pop these two things off, so both of these are gone. And we're going to carry out the operation 2 plus 3. The result is 5. That's pushed back on. So both of these are gone, so when we push back on, there will be a 5 here. And that's what we do with the plus. But that's not what you do. That's because with an addition, you work from left to right. That as you hit this addition, when we hit the next addition, it's time to go back and do this one. And that's true about the addition, the subtraction, the multiplication, and division. It's not true here. The value of this is not doing this. The 2 cubed is 8. So this is wrong. 2 cubed is 8, and 8 squared is 64. That's wrong. In fact, the way that works, 2 caret 3 caret 2, you do this first. And so we're going to have 2 caret, well, what is 3 squared? 3 squared is 9. Okay, so this is right. So you do this operation first. 3 squared is 9. 2 raised to the 9th power is 512. So this this place here, where we've got a 2, the similar place, so that's plus, incoming plus against plus on the stack. So the similar place is incoming caret against caret on the stack. This place right down here. That's not going to be a 2. If it's a 2, you'll get that wrong result. But if it's not a 2, what is it? Oh my gosh. It's a 1. And so that what happens then, if you have 2 caret 3 caret 2, yeah, you're going to have the I stack is going to have the 2 on it, it's going to have the 3 on it, and the O stack is going to have the sharp on the bottom and this caret, and we're right here at this incoming. And so the incoming is a caret, and we're going to put that caret on there. And then we're going to get that 2. And then what's there at the end? There is our friend the dollar sign. So when you hit the dollar sign, what do? You're at the end of the input. So it's time to pop everything off and carry it out. So when we pop this off, so now we're doing a 2, right? I mean, when the incoming is a dollar sign, we're pretty much finished here. If it's a dollar sign and we have any of these things, so I'm saying, yeah, if it's when you finally get to the dollar sign, it's time to do the 2 operation. So we're going to be, let's look at what happens then. Okay, so now the incoming is a dollar sign. And so we're going to pop this guy off. So we're going to do a power, and we're going to pop these 2 things off. This comes off first. The 2 comes off first. The 3 comes off second. So we're carrying out this operation here. This comes off, it's this guy. This comes off, it's this guy. We're going to do 3 caret 2, and so that's a 9. We're going to push that result back on. And so in place of this, we're going to have a 9 and a 2 sitting in the I stack. We've just done this. There's it now that we still have the incoming as a dollar sign, and we have a caret. So again, it's that second operation. So we're going to pop this off and this off. We're going to have the 9 coming off first and then the 2. And so we're doing this operation here, and that power is 512. Okay, so that's how it should go. So you should have this tomorrow. This is, you should test it out and make sure it works. Is there a question here?
I think he's wondering if this is homework. I think it is.
Well, yeah. This is the last thing about this. Yeah. So you need to have it. You need to fill in that table, that bottom row, and that right-hand column, so that the thing works. What changes did I make? It says I modified. Oh yeah, I put in this stuff up here. Yeah. Okay. So this is what should happen. No input files. Okay, I was going to show you this thing working. I guess. What? Oh, yeah, that's right. That's where yeah, fine. So I don't want. I guess I'm not going to be showing it to you working. But what will work then, once you have the appropriate numbers, is if you do put in 2 caret 3 caret 2, you should get 512. Parentheses should work, and so on. I think let me go back to the other. So we tried a number of these things the other day. If we put in 2 plus 3 times 4 carrot. Oh, the carrots won't work. I'll just stop with that. Yeah, that. It did the multiplication. 3 times 4 is 12, and then 2 plus 12 is 14. We could put parentheses in, and we could say parenthesis 2 plus 3 times 4 $sign. So this is saying do what's in the parentheses first. So we're going to have a 5. So 2 plus 3 is 5, and then 4 times that is 20. So as is, this thing is working. It just doesn't have the exponentiation. More complicated things, yeah, you should be able to say things like 2 parentheses 2. Oh, sorry, we restarted a dot out. So parentheses 2 plus 3 times 5 plus 6 $sign. So what should we get here? 2 plus 3 is 5. 5 plus 6 is 11. We're multiplying 5 times 11. We should get 55. So this thing is working correctly, and what I'm asking you to do is extend it to the powers, and so I mean the thing is, you can have parentheses inside of parentheses. I mean, that's really ugly. What's its value? So, I mean, humans really don't like to work out things like this, but 2 plus parenthesis 3 plus 5 minus parenthesis 7 times 2, and then I have 2 more closed parentheses developed. Where do you start? You start the innermost parenthesis, so that's 14. We've got 2 plus parenthesis 5 minus, so 3 plus 5 minus, this is 14. And so inside of this parenthesis, well, 3 plus 5 is 8. I'm subtracting 14. So this number here is what? It's 8 minus 14, that's minus 6. So I've got 2 plus a minus 6. So we should end up with a minus 4. I'm hopeful. Yeah. So this thing works. It's doing math that's, and it takes no time at all to do these expressions. The other thing we could do is we could easily add in variables. But maybe that's enough on this on this particular project. So you have a fairly small thing to do. Which is to add. So this is what? This is eval exp2, and you need to convert some of these zeros in this bottom line and some of these zeros in this right-hand column. You need to convert them to ones and twos. Not all of them, but some of them need to be converted. Okay. questions about what needs to be done for tomorrow. And one way to check that things are working, put in some ones and twos and try it out. That's how I'm going to grade you. I'm going to try it out. So that's pretty much it on evaluation of expressions. Again, it's a important part of what a compiler does. The compiler takes expressions and does this conversion. When people first wrote compiling, what are the very first programming languages? What do you know? So you had assembly language very early on. So that's basically machine language. What came after assembly language? So this is the question, just knowing a tiny amount of history. What came after? Well, C came on a little bit later, but IBM. So C was what? That was.
Talking about like basic.
Basic. Okay, yeah. C and basic are early, but there's earlier languages. C, that's AT&T, right? AT&T. That's Bell Labs. But there were earlier languages.
Talking about what pneumatic or first computer that they built.
So yeah, you have assembly language. What was the very first computer company?
No, I was thinking of like Alan Turing.
The first computer was built during the war.
Yeah, it was Alan Turing's computer, wasn't it?
Yeah, well, that was a very special purpose computer. It did one thing, it broke codes, right? And also you had computers that computed where ballistics, where if you shoot something up into the air at a big shell, where is it going to come down? And you have to consider things like air resistance, and you have to consider things like the fact that the Earth is turning under this thing as it's moving. Okay, so yeah, so ballistics computers. Yeah, and some of the general purpose computers were built at universities. University of Illinois had some of the early ones, but other places also. But there's some very famous computer company that IBM, yeah, IBM. And IBM is associated. It's not that I love IBM, but IBM is associated with some very early programming languages that they said, well, assembly language is too hard for people. And so one of the languages was COBOL, but I'm actually interested in another COBOL. That was written by Grace Hopper, one of the first women computer scientists. She was I think she was in the Navy. Grace Hopper. This will not be on any test. I think it's I think it's 2P. And then there is another language. It's Fortran. You heard of Fortran?
I think so, yeah.
What is that name short? It's actually combining two words. What is it? How about formula translation? So it was concerned with translating formulas into code that would compute those formulas. Formula translation. That's basically what we're doing here. If we added in variables, which wouldn't be too terribly hard, we would be doing formula translation. They were very concerned with producing code to calculate formulas that was as efficient as, so they were trying to do it automatically, that you could put in things like 3 times x squared plus 7x, 7 times x. And that the code that would be produced, so this would be converted to assembly language. They were very concerned that their automatic translator, this Fortran, this automatic translator, was going to be as good as what humans could do.
Usually we're going to need those for
Yeah, formula translation. So I mean, Fortran was a full-blown language. BASIC is kind of like a simplified version of Fortran. At least that's how it started. It changed a lot.
Who made Fortran? Does it really matter?
What?
Doesn't matter that we know who made that.
Yeah, that's John what? John. Be good to know that name. But yeah, because you'll be tested on it, sure. Yeah. John, are you looking for it?
Bacchus. Something like that.
Bacchus.
Yeah, that's the
Bacchus.
one.
Yep. So Grace Hopper and John Bacchus were the head of very large IBM teams that produced these first two high-level languages that got away from the assembly language. Yep. Fortran is still used for what? Scientific computing. And what about COBOL? COBOL has not gone away. COBOL, lots and lots of businesses use COBOL. I forget what it stands for. Common, I don't know, maybe the B is actually business there. I forget. Okay, so what we're doing here then, this is a form of formula translation. Okay, but we're through with this topic when you finish your so you need to add to then this EX, the eval EXP2. And once you put in the appropriate ones and twos in the bottom line in the right-hand column, your eval exp2 should work with all these operations, including exponentiation. Okay, that's. So we've got other things to do, and there's a significant portion of the semester left. We've talked about stacks. That basically you have kind of three possible operations that we've looked at on the stacks. There's the push operation, where you push a value onto the stack. So whatever, say X happens to have a 7 in it, then 7 is put on top of the stack. There might be a bunch of other things here. That's the push operation. And then there's the, push looks like this. It doesn't return anything. And code. And then there's the pop operation that removes a value. And so if we stick with the values being integers, so the values could be anything, int pop. So pop removes something from the top of the stack. So the top goes down one. If I pop something, this is no longer here. And the next time I'll pop whatever was under the 7. So int pop, this returns the value on top of the stack, and it's gone. The stack is now one shorter. So push operation, the pop operation, and just top. This reports back what's on the pop changes the stack. If the 7 was on top of the stack and you do the pop, the 7's not there anymore, and what's on top is what was under the 7. This top function returns what's on top of the stack, but does not change the stack. It just reports what's there. So these three operations, push, pop, and top, are what go with a stack. We implemented the stack how? We implemented the stack with an array that when you pushed something on, so we had two things. We kept track of what index. So here's index 0, index 1, index 2. And so we kept track of where the top was. So the stack was implemented as an array. We really had two things, an array and an index that, let's say we had an index t as an array and the index of the top. Was implemented as an array, so we kept track of, so we have maybe int t to begin with, it's like -1, the stack is empty. And so I've got this is the index of the top. And the other thing, okay, and then we have the array itself, int a brackets 100. So we have an array of size 100. So I mean, there is a problem with this. Maybe you push more than you want to push more than 100 things on the stack, and so then you would run out of room. So I'm assuming that at least on the expressions, I forget how big we made our stacks. Let's see. Was it 1,000? That seems pretty safe. Yeah, I guess the stack size, oh, no, stack size is 100. Here. So that's what this is, STKSD, stack size 100. So what did the push operation look like? So it doesn't return anything void. Push int some value. So what are we going to do here? We are going to increase t by 1. So we'll do t plus plus. So I'll go from -1 to 0. And we'll say a brackets t is going to equal to 8. So this is the push operation. We increase the index of the top, and with that new index, we could be on top of the stack. Pop. We want to return whatever's on top of the stack and make the stack one smaller than it was. So you can say return a brackets t minus minus. Oops, I don't really need a parenthesis there. Okay, here we go. What does that do? How does that minus minus work? It makes T1 smaller. Okay, so we do T minus minus, it does make T1 smaller, but what is the value of this thing?
It returns the value before the decrement.
It returns the value before the decrement. So the A, when I'm doing A brackets T minus minus, I'm finding what's on top of the value that's returned here is not the new value of T, but the old value. And so what I return, so I'm plugging that into A, so I'm getting what's on top of the stack, but now the stack is one smaller because we've done the T minus minus. Okay, so this is the pop code, and then obviously the top will just report what's on the top and not change the stack. So this is a way of doing a stack. What we're moving to here, we're moving to other ways of doing the stack, and in general, we're moving toward a little bit more toward C++. So what I'm going to do here is we're going to redo the stack using what is called a linked list, which I don't think we've talked about here, have we? Linked list. Okay. So we're going to talk about different implementation for stack, and we're going to be using instead of using the GCC compiler, we're going to be using the G++ compiler. Let me get out of this. So this remaining part of the course, then, we're going to be looking at various types of data structures. We're going to be doing stacks, we're going to be doing queues, and one or two others, a fairly small number. And we're going to be using this compiler. So what's a linked list? A linked list consists of two things. So there is a variable that keeps track of the beginning of the linked list. Normally you call this head, but the name is up to you. And we have a bunch of boxes. Each box, there's a room for data, and there's a room that keeps track of. So there are two things in each box: a place to store data and a place to store the address of the next box. So this thing right here, I'll call it next. It's the address of the next box. So we might have, we're going to keep our data simple. There might be a 7 here. Over here, there might be a 23. And maybe the last item in our linked list might be a 14. How do we know it's the last item? That's what we put in next. So this next has the address of this box. This next has the address of this box. And what's going to be stored here is going to be a 0, which means there isn't another box. So first thing we're going to do, so we'll just call this linked list. So linked list dot c. So I mean, it seems to me there's a pretty good reason why you have this name. So what's head? Head keeps track of the first item. So head contains the address of the first box, or if there aren't any boxes, or a 0. A 0 meaning that what? That there aren't any boxes. The list is empty. So the address 0 is special. It means that it's the address of nothing. We don't have any boxes. Okay, so let's see here. vi linked list dot c. So the first thing I'm going to do is set up these boxes. So we're going to set up a struct, and the name of the struct is going to be box, open brace, close brace. And so what's going to go in here are the two things we're trying to keep track of. We're trying to keep track of a place for data and then the address of the next box. And so what I'm going to put up here, int data, so that's the first item or field. And then the second item, what is this? This is a place for, this thing here is, the next should be the address of the next box. And I think we've talked about this before. Int x, that's a place for an integer. Here's x, and we're going to be putting an integer in there. If instead I want y to be the address of an integer, how do you say that?
And use a and
Well,
operator.
that finds an address, but if I've got an address, so the thing is that an address is an address of a place in computer memory. You know, here's computer memory. Way over here might be address 0, which we don't get to use. In fact, we use 0 to mean that that's the address of, you know, no place. Address 0, address 1. The operating system uses these low addresses. We don't have access to them as regular users. So then we have our space of memory, and inside of that, we can talk about the address, for instance, of x. And if you have the address of x, so if you have x, what kinds of things, you're used to doing all kinds of things with x. You can say x plus 3. What does the computer do with x plus 3? It looks up what's inside of x, adds 3 to it. It doesn't change x, right? It looks up what's in x. It gets the value of what's in x and gets the 3 and adds them up. Where? In the CPU. X hasn't been changed. It just looked that up. Or if you write out this, if you say x equals, that changes x. So this is a lookup operation. We look up what's in x and bring it back to the CPU. We take a copy of what's in x, bring it back to the CPU, and add 3 to that copy. X itself hasn't been changed yet. If you write x equals something, then a value is computed and then it's stored into x. These are the two ways that variable x gets, so in x, these are the two ways variable x gets used. One is a lookup operation which brings a copy of x into the CPU, and we do something with that. The other thing, x equals, well, a value is computed and then is stored into x. That changes it. If you have another variable that has the address of x, so say y doesn't contain, let's be very specific here. Maybe the value inside of x, so int x equals 7. So here's variable x. It has a 7 in it. And say I've got another variable y, and what's inside of y is the address of x. So you indicate that. Look at this picture. This is something you've got to know how to do because you have to be able to think about these things. That y, so x, the content of x is a 7. The content of y is the address of x. So y refers to x. That's what's meant by the arrow. Y refers to x. So how, if I say asterisk y plus 3, the asterisk is the dereference operation. Asterisk y is exactly as good as an x. It means x. So if y happens to have the address of x, asterisk y is x. And it works both ways. I can say asterisk y, just like we can say x plus 3, we can say asterisk y plus 3. And just like we say x equals, I can say asterisk y equals. And what's that changing? It's not changing y, it's changing x. So it's an alternate way of talking about x. So this asterisk, asterisk normally means multiplication, but multiplication always involves two things, something times something. So if I'm using it by itself, then it means dereference. Okay, so over here, I'm going to write box asterisk next. That's one of the things. Notice I'm going to be putting a semicolon. So I'm going to talk about this line here. But what about this? There's a semicolon at the end. It's important to remember that semicolon at the end. Okay, so there we go. What's a box? not next. Asterisk next is the box. So what does next contain? Next is going to contain, doesn't contain anything yet, but it's going to contain the address of a box. So we're going to write a little linked list. So this doesn't really much involve C++ at all. So int main. The other thing we need is we need to keep track of where this linked list starts. So that thing right there, that's a box, and we're going to be making a bunch of these boxes. And so I need to keep track of the very first box. I'm going to say here box asterisk head. And to begin with, I don't have a linked list, so I'm going to say that I'm going to make that equal to 0. Now, it's important to understand, this is the one exception. Every other time, when you write asterisk x equals, I'm changing x. But this is the definition of a variable. And so the 0 isn't going into asterisk head, it's actually going into head. Definition of a variable, head has a 0 in it. So every other time, other than, how do you know this is a definition? Boy, that's a difficult question. So let me continue the comment down here. Otherwise, 0 goes into, not into head, it goes into asterisk head. So something special is going on here. This is because C programmers are lazy. This is in place of saying, okay, so again, why is this a definition? I'm looking for, let's look up here, let's look at this line. Why is that a definition? Int data.
So you're initializing a variable?
Yeah, well, because you've got the word int there. What is that? That's a type name, right? That's a type name. Box is another type name. We are setting up a new type called box. So the reason this is the definition is that we are starting the line off with the type name, and so the type of data. So what kind of thing is data? Data is a place to store integers. What kind of thing is asterisk next? Asterisk next is, the type of asterisk next is a box. So, okay, good. So down here, what kind of thing is asterisk head? Yeah? What kind of thing is it? It's a box, that's right. This is a definition then, because I've got a type name here. And so this is in place of what C programmers, you'd have to say box, asterisk head, and then head equals 0. Well, C programmers are lazy, and so they don't like to do, so this is, that one line up there puts a 0 into head, and it sets up head as a place for an address. So why are we putting an address as 0? Because right now we don't have a list. We don't have any boxes in it. Okay, so so this is the this right here is the alternate way of doing things that C programmers hate because they're lazy. Well, I don't know, maybe not all C. I'm lazy. Okay, so let's see here. Great. So let's make ourselves a box. So here's some, time is up, right?
Yeah.
Yeah. Shall we make a box? Let's make a box. In B, box, asterisk in B equals new box. So there's a new keyword for you. It's the keyword new. What's going on? New says to the operating system, give me some room. How much room? Give me room for a box. A box consists of a place for data and a place for the address of the next box. Yeah? And what happens? So new. Give me a new box. Give me a box. And more than that, new return the address of the new box. Okay, so tomorrow then, in that other room, we're going to make ourselves a linked list. We're going to put data in it, and we're going to print the data out. Okay, so that's it for today. Sorry, it's 2 minutes over.